Good morning. So, I've gone through your documents, and I've looked at the observations and questions you guys have. The observations really all fell into three general things that you guys noticed. Technically four. There were a lot of comments about me wearing a hat in school, which is a normal thing that I do. But other than that, we had the mixtures changed their temperatures by a similar amount. One was 10 degrees down, the other was 11 degrees up. That's very close. Another observation was that the potassium hydroxide got foggy. Some people noticed that both of them got kind of foggy, but the potassium hydroxide was definitely more so. And then a lot of people noticed that there were different amounts in each. Thinking things like, if I had the same amount of liquids in both, how would that affect it? If I added different amounts of mass of each chemical, how would that affect it? Those are very interesting ideas. Let's look at the questions. So the first and second questions are the obvious ones. Pretty much everyone asked some form of these two questions. Why did the ammonium nitrate get colder? And why did the potassium hydroxide get warmer? Well, let's start looking at that. I'm going to bring you over to my other whiteboard right next to me, and we're going to look at a heating curve again. Okay, so remember, in our heating curve, we're able to look at the relationship between energy and temperature. What we started at was around 22 degrees Celsius. So we'll put that right there, 22 degrees Celsius. Now, the ammonium nitrate went down to about 12 degrees Celsius. So that would be here, 12 degrees Celsius. And the potassium hydroxide went up to about 33 degrees Celsius. So they changed by a very similar amount. A lot of people noticed that. That's a very good observation. So at this part of the graph, we don't have any freezing, we don't have any boiling. That's very helpful to us, because what that means is we can track our change in temperature and see that that is also a change in energy, that it is a very closely correlated value. So looking at this, I would say the distance between these dotted lines on the x-axis, that's going to be a change in energy. So to go this way, I had to increase my energy. To go this way, I had to decrease my energy. So why did the ammonium nitrate get colder? Well, it got colder because there was a decrease in energy. But what does that mean? What energy were we starting with? What energy did we finish with? If that energy decreased, where did the energy go? And if the potassium hydroxide increased, well, there must have been energy coming from something. Where could that energy come from? Now, what we need to remember is that temperature is that kinetic energy within those molecules. So all the little water particles, let's go ahead and use black for this, all the little water molecules, let's put one right here, put one right here, put one right here. Okay, so this is just starting out. This was the room temperature water. They're moving around, they're random, they've got decently sized arrows. When we added the potassium hydroxide, where did I use black for that one? Whatever. Use red for it. Red for potassium hydroxide. When we added the potassium hydroxide, it got warmer, so those arrows would get longer. Okay. When we added the ammonium nitrate, those arrows would have gotten shorter. We would have had less temperature, less kinetic energy in the water. Remember, we draw those arrows going in random directions. Good, good, good. Okay. So we would have seen an increase in kinetic energy going from the regular water to the potassium hydroxide water, and we would have seen a decrease in kinetic energy going to the ammonium nitrate. So why is that? Where would the energy go? Where would it come from? Well, remember, we have two types of energy. One is kinetic. What was the other type? We must have had a change in that type of energy in order to see these types of energy. We'll go over more of that on Monday. Okay, so we're going to save these questions for later. They really come into where did the energy come from? So we're going to carry that question forward. All right, why did they dissolve? That is a great question. Have you ever poured salt into water or sugar into water, something like that? Those will both dissolve. That also brings up the question, would it dissolve without stirring? Let's look at what dissolving is. At the risk of getting too complex, I'm going to look at what it means when a chemical dissolves. So keep in mind, in these little beakers, I'm going to draw a larger one so we can really look inside of it. We've got all these little water molecules. And what they're shaped like is like this. Water molecules have a bent shape. What that does, specifically with water and similar substances like water, is it causes one side of that molecule to be a little more positive than the other. Remember charges when we were dealing with ions. Water has a very similar property. Instead of being two separate molecules where one's positively charged and one is negative, water just has that change over its entire body, really. It's like, if you can think of a magnet. Water is like a tiny little magnet where one side is negative, one side is positive. Just like in a magnet, one side is the north side, one side is the south side. And that will cause it to attract or repel other magnets. So in water, the hydrogen side is positive, the oxygen side is negative. Okay, so that's what you need to know going in. So when I have something dissolving, like let's look at the potassium hydroxide. I've got KOH. Well, that's an ionic compound. Remembering back to ionic compounds, one of them has a positive charge, another has a negative charge. The K is going to be a positive one. The hydroxide is going to be a negative one. Okay. So this could be split up like this. Just like that, K and OH. So what happens when I drop this substance in here, I'm going to use two different colors just to try and help it be clear, is I've got K and OH, and then I'm going to write this, let's say this right here, is the surface of the water. And this is going to get dropped in. Okay. Once it gets dropped in, my water molecules will surround it on all sides. And then because these water molecules act like a little magnet, they have their own positive and negative sides, they're going to interact with the positive and negative ions. So I'm going to put my hydroxide right here, and that's got a negative charge. I'm going to put a little box around it so we can all give it a little barrier. And I'm going to have my potassium. That guy. Remember, that guy's got a little positive charge. So then my water molecules will surround that. So since hydroxide is negative, all of my water molecules that get close to that one will arrange themselves so that the hydrogen is closer to the hydroxide. Just like that. So each of these is a little negative on the outside and a positive on the inside. So now, within my little solution, I'm going to have all of these water molecules kind of carrying around this hydroxide. The same thing is going to happen for the potassium, except instead of the hydrogens facing it, it's going to be the oxygen facing it. I don't think I'm going to be able to draw as many because I'm running out of room here. Okay, and then the oxygens have that negative charge, and the hydrogens have that positive charge. And so the same thing will happen. And so these water molecules will actually split up each individual ion. When that happens, this dissolves, and because these individual ions are so tiny, we can't see them anymore. That's why at first I've got these big chunks in there, and then it starts to get kind of foggy, and then it starts to get clear. When it fully dissolves, it will be completely clear. We'll have a colorless solution. It'll be totally clear, okay? There is a special way to write a change like this with a dissolving. The way we do that in chemistry or other sciences is we write it just the chemical going in, and we give it that arrow saying that it's got that change. What I'm going to add in here is I'm going to put a little S to see that this KOH is currently a solid. Above this arrow, I'm going to write H2O to say that the change that's happening is this solid is being put into water. That doesn't necessarily mean that it reacts with the water. On the other side, I can write this two ways. There's two ways to write this. One is a little quicker, one is a little more accurate. So the first way is I could write KOH, except instead of writing S for solid, I'm going to put a little AQ for aqueous solution. That's a bit of a mouthful, isn't it? All that means is after I dissolve all that potassium hydroxide in the water, I now have what's called a solution of potassium hydroxide. I have a bunch of potassium hydroxide in water. That's all that means. When we talk about solutions in chemistry, we just mean we have a bunch of stuff dissolved in water. And it's so common that things are dissolved in water. I mean, think of the ocean, think of most water you drink has some amount of minerals dissolved in it. That actually helps with your thirst and with your health. That's all that means, that aqueous, that's all. But the more accurate way to write this, so I'm just going to write it down here, H2O, is going to be to split those up into their individual ions, because they do get split up. So I'm going to have K plus OH minus. That's it. So, when I have something dissolving, what's really going on is I've got the solid form getting broken up into its individual ions. Okay? So then let's look at the ammonium nitrate. That's NH4, NO3. Now we haven't looked at this before. This is another one of those that has multiple elements making up the ion. We did look at ammonium before. That was we used ammonium chloride in our original beaker freezing experiment. So ammonium, right here, this guy right here, has a positive 1 charge. Nitrate, this guy right here, has a -1 charge. So if I take ammonium nitrate and I dissolve it in water, then I'm going to get NH4 plus, and then NO3 minus. Just like that. It works the same way. It gets dissolved the same way. That's what's physically happening when I drop these solids into water. How do you think this change right here interacts with that energy change? How do you think those are related? Okay, so now we've looked at why do things dissolve? If you have any questions on that, feel free to ask them in either the chat or in a comment below, okay? So, stuff dissolves. I'm just going to say that for now to sum up what we just talked about. Stuff dissolves. But is dissolving a physical or chemical change? Well, if you're paying attention, notice we don't have any bubbles being created, we don't have any color change, I didn't have any smells happening. I know you couldn't smell it, but there was no smell that came about from dissolving this. Do we have any evidence of a physical or chemical change? Well, as far as chemical changes go, the only evidence is we had this solid disappear. But our ultimate proof of a chemical or physical change is going to be, is this permanent? So if I'm going to bring you back over here. So if this change is permanent, what that means is if I take away the water, I'll still have these ions separated. So that's one of the things I'm going to do. Over the rest of this week, I'm going to leave these beakers sit. I'm actually going to put them in my drying oven, and I'm going to let all the water evaporate out, and we'll see if this reverses itself and goes back the other way. We'll find out. If it does, then we have a physical change. If it doesn't, if this change is permanent, we have a chemical change. Okay? And then that'll answer, does this phenomenon only happen with reactions? So this one is, let's find out. And an exclamation point, because I am excited to find out. Okay, next question. Did the amount of water affect it? Let's see, I think there was another. And then number 9, did the amount of water in the beaker matter? So those are the same questions. Shame on you, Chesky. Should have double checked that. So the answer to that is, I don't know. Let's find out. That'll be a really good follow-up experiment. We'll be able to take both of these, and we could adjust the amounts of water, we can adjust the amounts of substance that we're putting in. Okay. So let's see. Oh, why? No, that number 9 was why did the amount of the water in the beaker matter? That is actually a very good question. So the potassium hydroxide, that solution, is actually one of the ingredients in making soap. My original plan was to take the solutions that we made from this lab and use them in a chemistry lab where we made soap. However, you guys weren't there, so we didn't make nearly enough. And the chemistry students aren't going to be there, so we're not going to make soap anyway. So, but that's why I used the ratios that I did, because it makes the right concentration. Too much water, and it wouldn't be concentrated enough. Too much potassium hydroxide, it would be too concentrated. You'd actually get a soap that would kind of burn your hands a little bit. It wouldn't feel good. Okay, and then, but what about the ammonium nitrate? That's a great question. That was more of a, I wanted it to change by about 10 degrees, so I went ahead and did the math. So we'll go ahead and we'll be able to look at that. How much causes a change? The big point that we're going to need to keep in mind is, remember when we talked about moles? The difference between mass and moles is significant here. If I have 10 grams of ammonium nitrate and then 11 grams of potassium hydroxide, those are really close in mass, but they might have a different number of moles, which remember is how many particles we have. What do you think is going to affect that energy change more? The difference in mass or the difference in the number of particles? That'll be something we'll be able to investigate. Okay, can this work with other liquids? The answer to that, what do you think? I think yes. There are a lot of other liquids, but it really does depend on the liquid. I could have something like liquid methane or liquid nitrogen. Those substances, they don't have that quality of water. Remember, water has that minus on one side, plus on the other. This is called polarity. Just like a magnet has a polarity, just like the Earth has a North Pole and a South Pole, it has this negative and positive poles. Not all liquids have that. So if I had something like liquid nitrogen, it would just be N triple bonded with another N. There's no polarity here because these are the same. They're not gonna shift their charges over one way or the other. And because of that, stuff would not dissolve in liquid nitrogen. I would need something that has this polarity to make stuff dissolve in it. That's why we have solvents, things like acetone, which that's what we can use to remove nail polish. It's very good at dissolving the nail polish. Things like ammonia can be really effective at dissolving dirt. That's why ammonia is a really good cleaning chemical. It will dissolve dirt, it'll dissolve those germs. So, can this work with other liquids? Absolutely. It just depends on the liquid. It's gotta be polar. Alright. Then can this be used for anything? As a matter of fact, oh my gosh. As a matter of fact, yes, it can be. Can this be used for anything? This is actually used in instant cold packs. I know there was one class that had that question about the beakers. Is this what goes into instant cold packs? The answer to that was no. The reason is because then the instant cold pack can't be reused, it can't be recharged, and it also creates a really bad smell. So what we do with instant cold packs is we have ammonium nitrate in them. When you activate it, you break open a seal that allows that ammonium nitrate to dissolve. There's enough of it to make it nice and cold for a longer time. And that's going to work on a sore muscle or something like that. Other uses for this, like I mentioned before, in soap making, it also has a lot of other uses just being on an alkali solution. It can be used in soil to bring the pH up if it needs to be. Ammonium nitrate also has a lot of use in agriculture. It is one of the primary fertilizer substances. For those of you taking agriculture classes with Donnerbauer, you've probably learned that soil needs nitrogen, potassium, and what else was it? I don't remember. But nitrogen is an extremely important chemical to get into the soils. The reason for that is nitrogen is extremely common in the atmosphere, but plants can't get it out of the atmosphere. It's really difficult to break that triple bond. And so we need to give the plants something in the soil, some way that they get the nitrogen more easily than with this triple bond. That ammonium nitrate, that's an ionic salt that has both sides of it have nitrogen in bonds that can be easily broken by the plant's natural processes. So one of the greatest inventions in the agriculture revolution was the development of ammonium nitrate. I'm forgetting my words here. There we go. So those are a few uses of these specific chemicals, and even a specific use of that process. In the production of potassium hydroxide, this temperature change actually needs to be taken into account, because if they do the process too quickly, it'll raise the temperature to a dangerous level, and that can cause big problems in industry. Okay, so there's no homework for the weekend. On Monday, I want all of those labs turned in. If you've already turned it in, great. If not, you have until Monday to get that into me. On Monday, I'll put it into the grade book. On Monday, we'll also continue on with examining these new questions. All right. Thanks, guys. I hope you have a great weekend. If you need anything, feel free to reach out. If you're at home and you're bored, I know it sounds crazy, but at some point, I imagine you guys are going to want more work to do. I can make that happen. Just let me know. If some of you need more work to keep yourselves busy, keep your minds active, and some of you do not, I can always make that division. We can always work that into this. So just give me feedback, how you guys are doing. If there's any changes you need made to these videos, like if you need me to talk more or talk less, if you need me to slow down or speed it up. By the way, these videos are on YouTube. YouTube has a little, there's a little gear in the bottom corner. I think it'll actually be over here. And that, if you click on it, you can adjust the playback speed to either speed me up or slow me down. I usually watch my educational videos on about 1.5 times the speed, because a lot of instructors waste a lot of time talking about useless garbage that I don't need to know. Like a lot of what I just talked about is probably useless garbage that you don't need to know. Some of you will like it, some of you will hate it. It's fine, speed through it. Great. If there is anything else I can do to help make this experience better for you guys, just let me know, okay? Thank you. I hope you're having a good time so far. I hope you're not having a terrible time so far at the